So by way of introduction, to those of you who don't know me, I'm relatively new around these parts. That's me, and the last name means what it sounds like, Wurm. And I've been a ham since I was in my early teens. But I was very inactive during my college years and my career years working. And my career years included some broadcast maintenance at Christian stations, KCAM in Glen Allen, KIAM in Nenana. And then mostly I worked for 36 years as an avionics repair guy. Had my own one-man FAA certified repair station here in town. But now that I'm an old retired guy, I've got back into the avionics, or into ham radio, and that brings us to magnetic loop antennas because it seemed like it'd be a good fit for my little lot where I have a house and no trees. So, but this is a discussion of my progress on this because I've had several iterations. Plan A over here, it's kind of hard to see, but this is the loop antenna. There's actually two loops here. This was made with house wiring, 3 conductors in a sheath. And then there's a smaller loop inside. This was about a 6-foot diamond or square shape, and the smaller loop was about 40 inches, which was covered 20 meters and above. The larger loop I was using on 80 meters and 40 meters. But it didn't work too well, and we'll tell you why in a moment. The current arrangement, or this is a picture of what is nearly the current arrangement. This is an 8-foot by 12-foot. So basically, if you're calculating a 10 by 10-foot square, but it's 8 foot wide and 12 foot high. Then there's a smaller loop, which is again 40 inches. This covers 20 meters and used to cover 15. And this is 80 and 40 meters. This is built using, as a structure, downspout. So you, what do you call that stuff? It's a plastic material, vinyl rain gutters. This is the downspout material. It's like 2.5-inch square tube and aluminum foil wrapped around it, and then it's covered with Gorilla Tape. But we'll get onto that in a little bit. So there's all kinds of magnetic loop antennas in the world, and you'll see some that are quite expensive, like commercial made ones. But then there's a bunch of home brew designs. Many of them use coax cable, the shield of an RG8 cable or something, as the main conductor. Most of them are like a meter in diameter. Some are bigger, some have multiple windings like this. But all of these, with maybe the exception of this one over in the far left corner, are very inefficient for various reasons. And although they work for portable operations, like when you're out at Parks on the Air or something like that, doing something portably, there's a lot of room for improvement. Now, my first iteration, I just kind of built based on some designs I had seen on the internet and, kind of copying some other people's ideas. And then I ran across a video on YouTube by this fella, John Portune. He's an old guy like us, but he gives a lot of lectures around the country at Hamfest and things. He's I think an electronics engineer, so he shares his knowledge with people. But he commented out these various factors that are important to take into consideration. So you've got the loop shape, loop size, conductor material. So the loop shape doesn't matter much if it's round or square or octagonal. The loop size does matter because you can't get, the loop has to be no larger than about 1/3 of a wavelength, and it can't be too small. And the conductor size is important. The size of I had originally my house wiring, maybe a 1/4-inch diameter all told versus a 3-inch diameter conductor. That's a big difference, as we'll come to. The structure, we've already talked about what I chose to hold up my thing. And then the tuning method and the matching tuning, because we have to tune this antenna to resonance, and matching, we have to make it match the impedance of my transmitter. So these are factors. Now, there are a number of pros and cons on any antenna system, but one of the pros, of course, for magnetic loop antenna is that they're usually pretty compact. Now, the one I'm using at my house is not one you're going to carry with you to the campsite. But in portable applications or with limited space, which is my case, they're a good choice. The negative side is because you've made things small, they have relatively low efficiency, but there is a way to get around that if you properly design it based on mathematical truth, rather than just hearsay, which is what my first iteration was. An advantage is because of the high Q resonance, you've tuned out a lot of extraneous interference. So you have relatively low noise received, but that comes with limited bandwidth. And it is quite limited, although it's not unacceptably so. You have to tune the antenna every time you move the transmitter frequency, and even with temperature changes on a large loop. So from morning time of 40 degrees, let's say, to summertime 90 degrees, there's a big difference in the tuning that happens. An advantage again is you can obtain one-to-one SWR wherever you are in the frequency range. Most ham antennas are compromised where they try to arrange it so that you have good SWR on the ham band, or at a portion of the ham band, and on, it'll cover several ham bands because they're usually arranged as harmonics. But with my antenna, I can tune it right to 5167.5, for example, which is the Alaska emergency test frequency. Many ham antennas won't do that. Of course, it does require precise tuning, and also another advantage or disadvantage is the loop antenna is directional. So if this was my loop antenna, you are in the null, broadside. Off the edge of the antenna, you have the maximum signal. Now this is, in my case, my antenna is not rotatable. It's up against the house, so I can't make advantages. But actually, this mostly affects ground wave. So for example, I have a friend sitting here, KL4TH, who is on the west side or the east side of town from me, and there's another guy, KL5SE, who is on the west side of me, and my antenna is arranged north-south, so they're both in the null. So for example, on 20 meters on JS8, that's where both of these guys are often there. They'll give me a SNR report of -13, -15, whereas I can talk to a guy in California and he says I'm +15. When I'm only running on 20 meters about 6 watts. So that's, of course, with good conditions. But the directivity, when it comes to skywave, gets washed out because the null is right here. But the angle of radiation is actually this way. So for skywave, even from the side, you've got pretty good coverage. And of course, it can be for ground wave a negative because it's directional. Now, I've always been intrigued with resonance. And when I got into radio years ago, everything was tuned circuits. And it was like there's a helicopter's rig over here. You had circuits that all were tuned circuits that had to be tuned together, right? Today we have all these broadband your radio is basically a bunch of bandpass filters. And if you got to get narrowed down, you use crystal filters to narrow it down. It used to be you had resonant filters. So here I have an AM radio, and here I have a loop antenna. And the magic here is resonance. So that's really what makes a magnetic loop antenna work. It is the high Q resonance. Now, while we're thinking about resonance, and broadcast radio for that matter, I've been in ham radio a long time. I remember as a teenager listening to shortwave radio from far away. And I don't know, maybe, can anybody identify this? You ever heard that before? This is Transworld Radio, signal from about the mid-1960s. The hymn is a trumpet quartet, I think. They're playing Stand Up for Jesus. It's a Christian radio station. They're no longer broadcasting shortwave from, this was Bonaire in the Netherlands, Antilles. But when I first heard that as a teenager, at that time I was also a new believer in the Lord Jesus Christ, and that really resonated with me. It was a different kind of resonance, but it really resonated. And at that time also, remember there's a hymn that stuck with me. It was, give the winds a mighty voice, Jesus saves, Jesus saves. Well, that's what this, broadcasting was doing. So I got into Christian broadcasting partly because of that, and other things. But anyway, we need to get back to our discussion here. So on to the mathematical truth of magnetic loop antennas. There are many magnetic loop antenna calculators on the internet. And this one, so far that I've found, is by far the best. So I've got the URL up the top there. But this one allows you to come to put in whatever parameters you want. The conductor diameter, that's the wire that makes the loop. The loop diameter, that's the dimension here. The number of turns, so that'll show up over here. We're using single turn right now. The turn spacing, the transmit power that shows up here, and any added resistance you might want to put in, but switch contacts and things that might be involved. But as you change those sliders, the graphs up here go crazy. They change instantly. So this is the default setting as you come to the website. You can choose also down here the units of measurement, metric or imperial. We'll use imperial on the next screen. The material for the conductor, copper or aluminum. Whether you want it to be circular, octagonal, hexagonal, or square. Well, I'll choose square when we get there. But here's the default setting. You have here a 1 meter wide diameter loop. And the conductor size is 19 millimeters, which is basically an inch. And this loop, they show, will tune from 0 to, this is about 26 megahertz. It doesn't really cover up through the 10 meter band. But here I've chosen to highlight this point, which is 14 megahertz. And it says the tuning capacitor is 42 puff, so tuning capacitor is here. The voltage across that capacitor is 6 kilovolts when you're running 100 watts into it. And the bandwidth, 9 kilohertz, I've actually found for my usage, it's a little wider than that. The efficiency of this antenna, radiation efficiency, is about 65%. That works fine at 20 meters. But notice this black line is the efficiency. So it's pretty efficient from 14 megahertz up. But down here at 80 meters, it's down about 5% or less. So there's quite a trade-off. Here's we've moved the sliders a little bit. We now have a square loop. This is similar, set up similar to my original iteration, you know, with the house wiring as my wiring. This is a 6-foot square with a 1/4-inch diameter cable or wire. So here, again, for 80 meters, the efficiency is quite low, probably about 5%. At 40 meters, it's improved, but it's not wonderful. Now I'll show you what it is later on, but we'll move on from here. Here's a, whoops. This slide is from a presentation by Mr. Portune, and he took a 4-foot square loop and comparing the different sizes of you know, the conductor. And for a wire, number 10 wire, it's really unusable for anything except maybe 10 meters. The commonly made loop with the RG8 cable as the conductor, the shield of that, is useful, but barely at 20 meters. But, you know, it improves with frequency. But a 2-inch wide diameter or 2-inch conductor becomes useful at 20 meters. But again, it's really useless at 40 and 80 meters. Although if you go out on your campsite with the thing and try to make some contacts, you probably make a contact. It's just not very efficient. Here is my larger loop, my current iteration. So we got a 10-foot square and 3-inch diameter conductor and a single turn. Well, that's what we show. But here at, let's see, this is 80 meters, 3.8 megahertz, about 68% efficiency. So we've come up quite a ways from what my original iteration was. That tells me the capacitance necessary to resonate. And I run about 10 watts, so now it's 2.5 kilovolts across that capacitor, which is easier to manage than 6 kilovolts. So I don't know if you have questions at this point. We'll keep rolling along here. This calculator you can play with all day, but here I played with a second loop. So you have these multiple loop antennas. Well, this will calculate what the efficiency is going to be if you spread those loops apart. So in this particular case, we've got an 8-foot diameter square loop with 3-inch conductor and 2 loops separated by 25 inches. And it's really not as wonderful as you might think, adding these extra loops. You can use it at 80 meters, and it comes up to about the efficiency of 68% of my single 10-foot loop with the same size conductor. But my 10-foot loop with that size conductor works on 40 meters, and this won't get there. Can't tune that high. However, let's see, somewhere I had written down, but I don't have it right with me now. You can expand the loop diameter on this calculator to 16.5 feet. And if you do that with the double conductors, the double loops, you can tune 160 meters quite nicely, but it becomes unusable at 80 meters. But if you have a single loop, like I have here, and you go to the 16.5 feet, with a 3-inch conductor, on 80 meters, it's about 85% efficient, theoretically. If you move that to a 6-inch conductor, then it's about 95% efficient, but it won't tune 40 meters. So my compromise is 10 foot and 3-inch. So we move down here, let's see. Well, here we have my original iteration, and you see how wonderful it was. 80 meters, 3.5% efficient. But I made some contacts. I actually checked into Sniper's loop, network a few times. 40 meters, better, but not too good. Over here, this is workable. 68% on efficient on 80 meters and 95% on 40 meters. I think you won't do better than that with a lot of other people's antennas. Now, I have other factors here that are poor, like being so close to my house. There's a lot of absorption into house wiring and stuff. But also I think that the efficiency here, this affects transmit. So if I'm running 10 watts, 68% efficiency, if everything was perfect, there's 6.5 watts going out, right? But coming back, this also I think will affect the receiver. So I don't hear as well as some people who have better antennas around town. Now the 40-inch loop inside is similar. I had on 20 meters, I had 40% efficiency. I've improved it quite a bit here with the larger loop diameter or conductor diameter. 21 megahertz, that's 15 meters, quite efficient. Right now I'm not tuning there, but I'll explain to you why in a little bit. But this was the situation. Now, a lot of these magnetic loop designs that you see, on the internet, use pipe, a copper tubing or something for making the loop. Well, a 2 or 3 inch pipe is pretty expensive if you make a 10-foot diameter loop. But you don't need to, because with RF you have skin effects, so all the current's flowing on the surface. So copper foil or aluminum foil is fine for the conductor, which is why I have aluminum foil wrapped around my my structure. Now, I will come to that. Now here is Mr. Portune presented a 4-foot loop with 1.5 inch diameter conductor. This will tune 20 meters nicely, but below that not too much. Now in his design, he's using PVC tubing or plastic pipe with aluminum tape on the outside. He has the capacitor is up here. This loop is a break right here, and inside this tube is a pipe that is pulled back and forth to form the capacitor. And he's done that in a couple different ways. He's got a device here to change it, to move that tube, and we'll show another method in a minute. He prefers this method of matching, which is a gamma match. There's a problem with that because you're fixed. Often on a gamma match, you have to move it even on a single band to get it to tune to best SWR. This is only going to tune one band. You're not going to get two bands out of this without moving that gamma match. So here's the way he puts things together. He's got his the structural member, wraps it with aluminum tape, then he puts aluminum tape inside the elbow, and that makes the contact to the next section. Well, I thought this is interesting because an important thing in a loop antenna is minimizing the resistance all the way around. That's why the larger diameter, it's RF resistance. is what you're worried about. But here you're coming down to these bottlenecks and places where when you get a little rain in there, you're going to have corrosion, and then you're going to have resistance. So it's not going to last too long in my mind as a efficient antenna. So therefore I chose to make my loop one continual length of aluminum foil, no breaks, which, well, here's on the structure first. Since I'm using this downspout material, the square downspout material, needed some reinforcement in the corners. They don't make a 90-degree downspout adapter, so you have to do something. So I made these aluminum formed things. These are just basically, it's very lightweight material like you'd use at the edge of a roof or something. There's a word for that that's escaping me right now.
The electrons have a harder time making a hard right angle through?
They don't seem to, but it could be a factor. Anyway, these are inserted and pop riveted. Now, because I have a 12-foot section, you know, my two vertical sections, and this stuff comes in 10-foot lengths, I had to splice them, and I cut off the 2 feet from the 8-foot and splice them onto my 10-foot to make 12-foot. So this is another insert. This is heavier material I used there. Then the top member, horizontal member of the loop, I inserted a bar inside the back of it with the nut plates to hold bolts that hold these clamps to my mast, you know, my plastic pipe mast. So that's the structure. Here is installing the aluminum foil on the small loop. I also protected the corners with tape where there might be some sharp points you don't want the tape to tear. And also, as I put the tape on, I left it a little baggy, so it's probably a little bigger than the actual design is supposed to be, because I wanted to accommodate expansion and contraction. The vinyl stuff has quite a range of expansion and contraction compared to the aluminum. This is the small loop. Here's the larger loop getting its dressing. I built a little jig to roll the aluminum foil off nicely, and every so often on the pieces I put some double-sided tape, so this is hanging in place before I started to fold it onto the thing. I built a little, the most challenging part of all of this is to make the pigtail that's going to go down to my tuner. You don't want to tear the aluminum foil, so I built a little guide to guide me as to starting the folds for making the pigtail, and kind of how to invent some things along the way there. Now, so there's the structure, the size, and the conductor size. Now we move to how we're going to tune this thing and match it to the radio. The most common method you'll see on the internet is this one over here, using a coupling loop, a single capacitor to tune the antenna to resonance, but then you have to couple it to the hopefully 50 ohm impedance of your transmitter. This always made me nervous. Usually, this is basically a short circuit from your center conductor to the shield of your coax. And so you don't want to put a short circuit at the end of your coax. Now, this isn't a short circuit. The inner loop is big enough, and if it's coupled to something that's resonant. But if you don't want to put this loop at the end of your transmitter with nothing there to take the load. So it makes me nervous. Besides this is awkward. The way you tune or you adjust the matching here is by moving this small loop closer to or farther from the big loop, and sometimes you have to distort that small loop in order to get the proper match. Well, there are various ways of doing it, but it's awkward mechanically. Then you have this method. This is probably the most common method you see on the internet. This is John Portun's method with the gamma match, but this length is critical, and the point of connection is critical for certain frequency or frequency range. So that's awkward, especially if you want to get several different bands on a given loop. This method here was actually used by a military antenna system in the Vietnamese War, where the men were equipped with a portable loop that was disassemblable. It was several lengths of copper pipe that screwed together, made an octagonal, or maybe it was hexagonal, but loop. And then the tuning box was the equivalent of this. However, they also had some fixed capacitors that you could click into the system. So in this system, you have the antenna is tuned by this capacitor and matched with this capacitor, matched to your transmitter. There is quite a bit of interaction between the two controls, but it's not something you can't deal with it. There's another advantage of this. You know, you've got, in my 10-watt situation, I've got 2.5 kilovolts across the capacitor, but when you have double capacitors like this, it breaks down that voltage, so you don't have that much voltage in the middle where I'm connecting to. So, capacitors. Often when you're talking about mag loops and the fancy ones in high power, people say, use these vacuum capacitors because they'll handle the voltage. Notice the gap that's necessary for an air gap capacitor to handle the voltage that will be found there if you're running high wattage. Well, another factor on the capacitors is, for example, here, you don't want to have any wiper resistance introduced because that increases the contact wipers. And a lot of capacitors, variable capacitors, have a contact wiper. So the butterfly capacitor, and there are different arrangements. Either of these are butterfly capacitors. Here you have the rotary plates on this section and the rotary plate on this section are connected by the solid shaft. There's no wiper. So you make your connection to the stationary plates on this side, the stationary plates on this side, and there's no added resistance in there. The same thing applies here. Of course, in this case, you have a butterfly-shaped rotor that fits behind the stationary plates, and it's shown, unfortunately, in the place where you can't see the other plates. Those are expensive. So I made my capacitor, or capacitors, using this method. This is 3 by 4 inch single-sided copper-clad printed circuit boards. And they're spaced here in the picture far enough apart you can tell that there's a difference between them, but in reality they're very close together. They're just a paper thickness between the plates or less. So we have, in order to get the kind of capacitors we need, I have 2 stationary plates, and these 3 movable plates are all attached together and they move as one. I have a motor, drives a drive screw through a threaded nut which is glued to this plastic block which isolates it from the capacitor, and so this whole section goes back and forth. And so the equivalent capacitor is here. I have this dotted line because in one of the capacitors there is no connection necessary there. So here we have no extra connection. We just have that shield connection which we have to make on one of the capacitors, and that's what this line is showing. Now, even this is simpler than what I came up with eventually, because when these plates are out of the way, these plates are still pretty close together. So therefore you have more capacitance between this plate and this plate than you really want. So I ended up splitting, what do we say, dividing down the middle of these stationary plates, cutting through the foil on the the copper cladding, so that I had separate on left and right. So here we have, if this was the whole plate being used for one plate and the whole plate here, here I have a dividing line between the left and the right section. So now you have one capacitor plate, one stationary plate, and another stationary plate. I'm not making this clear maybe, but you follow what I'm saying mostly? But anyway, this is this is the arrangement that I have. Transmitter receiver is wired in here. I have a flexible braid which connects to the movable plates. That's the only connection to the movable plates anywhere. And this is the equivalent circuit. So if you follow what the diagram was up here, we have, these are the connections to the braids to the two loop, from the two sides to the loop. Whoops, that's this one. So braid to loop, and the other is the connection to the transmitter. Okay, here's a picture of not the finished product, but a product in the process. So on the left side, we have the stationary plates. Right side here is the movable plates, the 3 boards on top of each other, fastened together. Back here you see the plastic block with the nut and the drive shaft, motors over here. Now I put this out in the tuner box. It worked fine for a month or two, and then it got cold. It stopped working. Reason was the expansion and contraction of my plastic block versus the metal drive shaft made the fact that I had 2 nuts here, it bound things up. Remove 1 nut is the cure. Now, with this, there is a stop switch, or an end switch, I should say, on each of these movable sections. End switch here, similar on the other side, so that when the movable section gets to the end of its travel, it doesn't jam up. And yeah, this is the tuning box and the controller. So the tuning box was made out of a display case for an Avionics Loran C radio, which were for a few years popular. But when they became unpopular, I have a little display box that was no longer useful for my business. So I threw it in a junk pile. And after I got back into this, made a wonderful case for housing my tuning box. Put a little door on it, and actually the plastic base for the tuner, it was actually a shelf that was inside of this thing. So here's the tuning mechanism, tuning capacitor arranged vertically. We have the motors down here, and this is the first iteration of the tuning box. At this time, I was changing bands, that is, moving from one loop to the other. With this little panel here was a bunch of banana sockets, so I had banana jumpers. I had to change to get from one loop to the next. And you'd push, well, there's a fast and slow button here to control the speed of the motors, just changing the voltage. And this is the buttons for adjusting the tuner, and this for matching. So you press the red button to get more capacitance, the green button to get less capacitance. When you get to the end of travel, the light will light up inside. So it turned green, you're at the end of the trap, right minimum. A couple of problems with this. It gets cold up here. And in fact, this is showing the 2 nuts in place. But not only does that be a problem for the 2 nuts and it jams up, but you got to go out and pull the jumpers out, and then you got to go out and figure out where's the capacitor. I don't remember where I set it last, and am I getting near where it needs to be for tuning? So this was lacking. Here's my house wiring coming in with. So rethink. This picture does show the separation between the plates, the cut down through the foil on the, and by the way, while I'm thinking of it, we have braids with the lug nuts or lug terminals. These are the connections to the loop. I added here these things, which are sliding resistors, variable resistors. You would find them on an audio control box, maybe a mixer. And what they do is they travel along with the moving parts, and there's a voltage divider, and it reports the voltage back to the tuning box. So here we have the tuning box improved. Now we have this displaying that we are at zero, that is minimal capacitance. So that's on the tuning capacitor. We're about mid-range on the matching capacitor. And let's see, you can also see the braid that connects the shield of the coax to the movable plates. So let's see. This is. You might wonder what these are. This is just nylon rope that goes through a piece of hardware that used to support the top of the old diamond-shaped wire antenna. But this is just to hold up, to help support the thing in the snow load and stuff. Here's my tuning box, and you see a little bit of a cover I've built around here. We'll get a better view of that in a minute, which is to protect the connections. So the connections are where we're at. This is the pigtail here coming down, the aluminum pigtail coming down from the small loop, this from the large loop. It comes into, just gets bolted in a fancy homemade arrangement, this terminal. The terminal was slid through a little slot cut in the side of the thing. So here you have the inside. Once the terminal was slid in, I bent it over, attached it to the case with a screw, and then have this wing nut to which I would move the my tuning braids, or the braids out of the capacitor, to either the small loop or the large loop. There's a problem with this. It gets cold here in the winter. And when you go out to try to work these things in the winter, you can't get them back on with cold fingers, and then you lose them in the snow. So this isn't going to work long term. Here's my better view of the cover over the terminals. So we made a relay arrangement to switch between the loops, which I won't go into great detail, but there's one relay here. You don't see the knurled, or the wing nuts anymore. There's kind of knurled knobs, and two relays over here. So what else can you see in this picture? Oh, we've added this stuff, which is heat tape, to warm up the inside of that box to prevent grinding up the little gears in the motors when it's 30 below. Okay, here's one of the relays. This was added because I found that in order to tune in certain places, we needed to really have a real ground. You're not supposed to need a real ground, but I added that. Okay, so here is the outcome here. So this is the switch added for switching between the bands. Toggle switch, 3-position. Up is small loop, middle is large loop, and down is both loops in series. And also I have this box here. The way I tune, I do not tune using my transmitted signal, because it's too hard on the transmitter, because these things, the loop antenna takes a bit of tuning and it's pretty sharp. So I use this device. It's an Arduino, which is basically a signal generator that also will measure SWR. So I dial in the frequency I want, push this red button, which disconnects my radio from the antenna and connects this through that to the antenna. So I make my tuning, release the button, and then I'm on the air with the radio to the antenna. Okay, enough there. It's helpful to keep a little chart of where the approximate tuning range. So these are the numbers that are shown on the digital readout, and you moved close to those, you dial those in when you change frequency, and you're nearby. I show SWRs here of mostly 1.0, which is 1-to-1, and bandwidth, my bandwidth measurements is like, if I get to 1.5 to 1, I figure that's the outside limit. And I don't know what you're supposed to use, but at 15 meters, 21 megahertz, I used to have 1-to-1 SWR. Now it's pretty messed up, 3-to-1. And also on 40 meters, it used to be 1-to-1, should be showing 1-to-0 here. It's now 1.2 to 1.5 because I've added extra capacitance with my relays and with another thing. This is showing the next iteration. I'm hoping that this will improve when it gets -20 because then the antenna will be smaller and it should not take as much capacitance. But you can see that you can tune throughout the range, getting pretty good SWRs. Okay, here's the next capacitance problem. I decided to add a 10-meter loop. So that's the little one inside the little one. Originally, I put it down on where you should see it on the left there because it was winter time, snow on the roof. Wife wouldn't let me get up there. So I put it there, and it actually worked pretty good. This summer, and last winter, there were some times when 10 meters were pretty good. This summer I was busy and 10 meters was poor, so I forgot about it. Well, sometime in August I decided I will move it up here because it probably won't interact with tuning as much as down here. I moved it up there and it didn't work at all. And it was actually resonating at 60 megahertz. Oh, fine, but I don't need it, and I couldn't tune it. It was just stuck there. So I took it down and found it was full of water. And that's a factor because the tuning for this 10-meter loop is quite different than for this loop with the tuning box. I ended up, after fixing it, putting it back where it had been in the lower location. But here's the 10-meter loop arrangement. So it's about 22 inches on the side. Again, using the downspout material as the structure, aluminum foil wrapped. But the movable plates for tuning it are inside the structure, and we use the structure as the dielectric for the capacitor. So the coax cable comes to some plates that are laid on, it could be foil, but on the one side of the structure in that area. I used brass because you can solder to it. And then the capacitor is formed by the moving elements against the gap in the foil. So you've got foil on all sides except the side that the brass plate is on. So this is the tuning capacitor. And then we have here foil on two sides, except a little bit more where we want the matching capacitor to interact with. Clear as mud. So here's that gap for tuning, and this is the side of the antenna showing where the foil has been adjusted for better matching. I tuned this originally in my shop with this small antenna hanging in the shop. Of course, there's equipment and shelves and stuff in there. It tuned up nicely. I had to change where this foil was, or fold it back from where you see here to there in order to get the match to work right. But out on the mast, it's all messed up from that. The matching really is, other stuff interacts. So this is the tuning capacitor movable element. It's about twice as long as what it looks here because of what's inside, but this is a square, 4 sides, whereas the matching element was 2 sides. Here is the whole structure of the tuner, the tuning block with motors, drive screws. This is in the what turns out to be the minimal capacitance mode, and this is maximum capacitance mode. There's a long shaft that goes all the way through. This is an aluminum tube which holds the stop switches. There's one stop switch, there's another stop switch, and the wiring for the stop switches. Now this is showing the structure for the matching capacitor. That's the nut that the drive screw works in, and these holes here allow the passage of this tube for the stop switches. This hole allows the passage of the motor when it comes in. Another view. Now on the large loop tuning method, I have the slider resistor that shows the relative position. There's no slider resistor here, but instead there's a little mirror on the inside of the movable pieces, and that reflects light from an LED back to a light-sensitive resistor. So again, it's a voltage divider, and it reports in the same way. It's not quite as reliable because things shake, and it's but it's usable. Here's the connection method to the control and reporting circuit. Here it is in the side of one of the structure. This hole accepts that screw, so you can tell where we're at there. And this is just the cabling into the control mechanism. When I found the water inside my 10-meter loop and had to tear it all apart, I found that I had designed it in such a way that if I had a problem inside the tuning mechanism, there's nothing to do but tear the whole thing apart. So all the foil comes off and you have to start all over again. So in the second iteration of that, this bracket here has a hole in the bottom of it that's big enough to accept everything that comes out of that tube. So I can get it all out, and also there's a drain plug to let water out. Again, it's covered with Gorilla Tape. On this loop, there are 2 brackets to hold this, to support it. There's a plate inside here with nut plates. So here we have the drain hole and the place you get the mechanism out of. And this shows the wrapping of the duct tape, or the Gorilla Tape. On the vertical sections, you start at the bottom and wind it up, and then it kind of sheds water. On the small loop, I decided that wastes a lot of tape. I'll just run the tape all the way down, and that sheds water. So that's something that I would do again probably if I had to mess with the big loop. So here is the tuner for the 10-meter loop. Now has a switch to decide whether I'm going to tune or match. And again, more capacitance, less capacitance. While you push the button, the display shows the number that relates to the position. And this box now has been a switch added to select 10-meter antenna or 80 to 15-meter antenna. Same thing, they'll push the button, use this device to tune, and then connect to the radio. So here is the tuning chart for the 10-meter loop. And you will notice we've added here, this is that tuner on the left, but this is the main tuner because there is interaction between the big loop and the 10-meter loop. You would think so because that 10-meter loop's right inside the 20-meter loop, which is connected here. I'm using both loops. So you have to tune the main loop too, but it's much less critical tuning for the main loop. Just get it in the area. And you would think, well, maybe that's absorbing the signal and it's not going anywhere. But I have worked with 5 or 6 watts on 10 meters, the east coast of the US with this. So it works when the conditions are good. So I guess that's about all I have to say on that. If you want to review, if you go to the QRZ.com, put in my call letters KL7HJF Hotel Juliet Foxtrot. On there is kind of a review of the of my magnetic loop arrangement. So I'm gonna be around if you have any questions on anything or want to discuss something, that's fine. I did have one additional observation that I wanted to make though, and that is an observation about ham radio in general. Well, I put a lot of time into this little project here, right? And you put a lot of time into your projects. And we spend a lot of time tuning around on the radio, trying to draw in weak signals and, and stuff. And we end up with logbook entries which have some guy who will never meet's name in it and his QTH and it may be his signal strength, but it's a very limited long-term value, right? So I would like to suggest, encourage that we take the time to tune in to God's Word, the Bible, because so that it can resonate in our hearts. And I'll close, kind of sign off with one brief packet from that sender, which says, as it is appointed unto men once to die, but after this the judgment, so Christ was once offered to bear the sins of many, and unto them who look for him shall he appear the second time, without sin unto salvation. So that has lasting value. I'll sign off. Thank you.
Thank you.